minutes, give or take. And then you guys should have a video. Please post the link in the chat. We'll all independently watch the video, and then we'll come back afterwards for a Q&A at the end. A couple notes. Please introduce yourself and what your major is at the beginning of the presentation to the judges. And also, please keep your mics off when you're not presenting to eliminate as much background noise as possible. Besides that, we're ready when you are.
So we introduce our majors first?
Yeah, just briefly introduce yourself and your majors, because none of the judges know you guys.
Hi, I'm Katrina. I'm an electrical engineer.
Hello, I'm Gabriel Smith. I'm a computer engineer.
Hi, I'm Chris Foley. I'm a computer engineer and a robotics engineer in SubMat.
Hi, I'm Carly Bowling, and I'm a systems engineer.
I'm David Guardiola, and I'm a computer engineer.
All right, is everyone ready?
Yep.
Hi, I'm Katrina, and this is Team Bear. I'd like to start by asking a seemingly simple question. How many fingers am I holding up? For people who wear glasses, this is a commonly asked question. But for approximately 4% of the population, this is even more frustrating due to the double vision caused by their strabismus. Strabismus is the medical term for cross-sightedness, and the symptoms include eye fatigue and strain, double vision, and eventually the brain's adaptation to cut out signals from the affected eye entirely, which results in the loss of binocular vision. Available treatment options include eye patch therapy, which has variable success and can be painful and irritating. Ocular muscle therapy, which is about 60% effective, but is also expensive. And binocular fusion exercises, which don't correct the root of the problem and are rather supplemental for the symptoms. The problem is essentially this. Imagine trying to read a book like this. Seeing double can be very disruptive in daily life, but VER can fix that. Now I'll hand it off to David, who will discuss our vision for a clearer future.
Building upon the idea of binocular fusion exercises, we set out to make a therapeutic software solution utilizing current-gen virtual reality hardware to help restore binocular vision, essentially granting the person depth perception. Our goal is to simply have the user put on a headset and look at the internal screens. From there, we track the dominant eye, track the non-dominant eye, and warp the non-dominant eye's screen to the corrected view based on their good or dominant eye's view. This is the strabismus affected eye inside of the headset. As you can see, there is a desired gaze that is based off where the dominant eye is looking. However, this eye is off at an angle from what they should be looking at. What VER does is warp what is shown to this eye in order to rectify the image difference between the user's two eyes. This is what we would call a full correction. A full correction is great, as it allows the user to instantly lose that double vision and gain depth perception back. However, from talks with ophthalmologists and physicians at CHOP, a therapeutic approach is far more viable, as it will allow a doctor to adjust the degree of correction over time to strengthen the eye muscle. To implement this, we needed a readily available VR headset with proper eye tracking capabilities. Now on to Gabe, who will walk you through our choice for the headset.
We went with the Vive Pro Eye from HTC. We chose this headset because it has a gaze tracking feature that gives us data on eyes separately, along with a 90Hz screen that will provide a comfortable viewing experience. It also includes some creature comforts, like dual exterior cameras and compatibility with 2 different eye tracking APIs, allowing for more features in the future. This is what we would use on human patients. However, while we have submitted an IOB so that we could test on human patients, in order to bring a mostly functional device to the tests, we would have to have a simulation of the suite. How that works is, in Unity, we have 2 screens and 2 gaze points, one each for the dominant and the non-dominant eyes. The dominant eye gaze point and both screens get input to the point-to-point converter, which gives the desired non-dominant eye's gaze point. We then feed this desired gaze point along with the non-dominant eye's screen and actual gaze point into the screen warper. which transforms the screen in such a manner that, when projected back to where the eye is currently looking, it should see what it would see if the eye had no strabismus. I will now hand it off to Chris to talk about system performance and constraints.
I'm not hearing anything. I don't know if anyone else is.
I'm not hearing anything either.
Someone's muted. Who's supposed to be talking?
Christopher Foley.
Yeah, he's talking. He's not muted, but I bet his headset's not working.
No, we can't hear
Your
you.
headset's broken. Or it's dead.
Can you hear me now?
Now
Yeah,
we can hear you. Now
we
we
can
can
hear
hear
you
you.
now.
Sorry. Thank you, Gabe.
No worries.
Here's a graph of measuring the effectiveness of our solution for various users. As you can see, as long as a user has some degree of strabismus, our simulation can partially correct their vision with minimal error. While it does not perfectly fix your vision, it is significantly more effective than not using the headset. The current latency for the system is 500 milliseconds on average. Ideally, we would have the latency on an order of a few milliseconds. The latency of our algorithm is linearly correlated to the number of pixels being displayed to the user. In summary, the good news is our solution is great at providing the correct image to the affected eye. The bad news is that our simulation is quite slow. Unfortunately, we have a few constraints. Apologize, this is not coming up. We do have, my phone script isn't coming up, but we have a few constraints. We have image noise due to the fact that if we were to shorten image capture time, this would increase error and noise. In addition, we are currently using a CPU-based image capture library for processing instead of a GPU-based library, which, while it would be quicker, would cost significantly more money. In addition, without switching libraries, if we were to shorten processing time, this would increase probabilistic error as a result of ransack. In addition, since we're working on a Windows computer, we also have error and average image processing delay errors. In addition, we also had to halt further production because of the coronavirus epidemic. Now I'll hand it off to Carly, who will talk about implications and standards.
Thanks, Chris. Had to unmute. Sorry. So there are some ethical and societal implications to the VAIR software that we've created, and these include the consumer price protection, as this would be used in medical settings, and due to the $39 million ophthalmologic therapeutic market, as well as the fact that parents are not typically price sensitive, we would not be immune from this common issue of price gouging in the medical industry. However, a more positive societal implication of our software would be the improved VR experience for recreational uses. As most devices are made for men, individuals with other optical conditions, in addition to smaller facial structures, could have a better experience using virtual reality due to the software. And as long as the frame rate is adequate, we do expect that this convergence assistance could actually limit cyber sickness in the future. And in order to see these implications, we really had to follow certain standards. The first of these being the IEEE VR AR working group. One of those is the 30 hertz minimum, which kind of piggybacks off of the ophthalmological standards, which include the 30 millisecond latency. And we also need to be able to handle plus or minus 10% angle variations in the eye, because that's what you'll typically see in strabismic patients. In addition, we had to write a consent form and go into the details of the ViPro-Vi specifications. And that's due to the fact that we did submit an IRB back in the fall for human testing. And lastly, we are accepted into the Andrew P. Sage capstone competition. And so we have to just follow the Systems Engineering 5 design principles, which are just a widely set of adopted principles for systems engineering projects. And lastly, looking to the future, we're really excited. Dr. Tyson Lawrence is someone that we've worked with on the more of the medical side of the project, and he thinks that the therapy is really innovative, and they don't have anything in other virtual labs that they use that has the capability that our software does. And so with that, I would like to thank you for listening to our presentations and understanding that we are all still adjusting. No matter how many times we practice, I feel like there's always something that comes up. So the technology.
Great. Thank you.